So we're on the 3rd of November, 2025 at 7 p.m, at least British time anyway, but it's great to see people from around the world. Forgive me again for my neck pillow, because I get getting a lot of neck pain. Anyway, so I'm quite excited tonight. Andrew, gosh, do you know how many Andrews got? There's me as Andrew Thornett, Andrew Sutowski, and then we also got Andrew Strong. This is Andrew Sutowski. Sorry, Andrew, to say your surname, but there's too many of us around. He's going to give us a presentation on 3D printing and anything else that he wants to talk about to start off our meeting. So the floor will be his, and then thereafter I'm going to move directly over. Obviously, a chance to ask him any questions you want to, as always. Then I will move to Ted, who's also going to give us a short presentation, or a long presentation, however long he wants to be, on some very exciting stuff that he's been doing with Ezra, and some real advances I think he's made. I've had the pleasure of being a beta tester for some of that stuff, so I know you'll enjoy that. And then, as always, I will go through the group one at a time, and everybody will then have a chance, if they'd like to talk about any particular issues that they want. And I also have an apology from Paul Hearn of the BAA, who's I'll just read it out because he has a particular question he wants to ask as well, or a few things perhaps. So he says, "I'm sorry I'll not be able to join tonight, but we'll watch the video without detention. I plan to update each of you, I suppose next month, as my H-Line project progresses." You had a question, so you may recall I had a question about calculating the offset angle of my dish. Thank you, Heather. Your link pointed me to a great resource, and I know the answer is 18.5 degrees. Had I been at the meeting, I would have reported on dish offset calculations, waveguide design and calculations for dimensions, and also demonstrate the elevation inclinometer I'm using as the dish is motorized using an MPU 6050. So I think we'll get that next month instead. But he has one particular question he wants to ask, which we'll not do now, but just we'll come back to a bit later, which is what cable specifications should I use for a signal line from the LNA to the SDR of about 15 meters. So we'll come to that a bit later when we're going through the group as a whole. So I move over. So hi, it's Adrian, isn't it? I think, hi, Adrian. Nice to see you. And we'll move over to Andrew Sutowski here, if you would like to start us off.
Okay. So, share screen. Share screen. Slideshows. Okay, so some of this is what I showed last time, but I've been playing around with 3D printed waveguides and feed horns, and the waveguide design that I chose was this one for H-Line from V4MA, and so it's got all the dimensions on it. So that's what I started working on the 3D printer with. And then I also found some information from the antennas lab about 3D printing and how you have to paint the models afterwards in order to get some reflection of the signal. And our discussions last time we went through this gave some more ideas, so I'll go through and update you on where I've got to. So to start off with, this is the initial feed horn made out of PET-G, so you've got a waveguide in the middle, and then because of the size of my printer, I had to make the choke in 4 sections, and it's all glued together. And then it's painted with this MG Chemicals silver coated copper spray paint to give you a nice reflective surface. And then you can start doing some VNA analysis on it, and you can see this is a 43 millimeter copper tube probe monopole, but on the raw plastic, and you can see the raw plastic has no real signal at all. But then when you paint it, you can start getting signals, and as you change the length of the probe, then you get better signal reception, if you like. And so between 47 and 48 was the optimum for this feed. So then I tried it out, and this is just using a 350mm aperture choke with the 158mm waveguide in the middle, and over 2 days you can see the signals you get, and you can see the bumps over time. And then on the right here I've got the maximum looking from left to right across the timeline, and so those are the signals you're getting at the appropriate places. So just a simple 350mm aperture, I'm getting good signals out of the painted waveguide. And so I thought, let's try and optimize this, because the spray paint is quite expensive. What I also did is I put 2 copper tubes, and if you then take the 2 copper tubes and you multiply the signals together in an interferometry way, you get better signal to noise. So if I flick to the next one, which is just 1 horn, you can see, and I'll flick back, you can see the signal to noise improvement you get by multiplying 2 horns or 2 feed horns, 2 monopoles together, rather than one on its own. So that's the second one, the first one, and then multiply 2 together. So this sort of what I call coherent interferometry gives you a boost in signal to noise. So then this is the old feed horn that I had, and you can see all the plastic layering on it has been coming off, and you can see inside the 2 monopoles that I was using on this one, but I was getting no real signals out of this. And so having done the 3D printed, I thought, right, let's pull this one off the dish and analyze it and see what's going on. And so if you do the VNA, you can see that it's giving some reasonable signals. And then if you put it and do some analysis just on the shelf, not on the dish now, you can see it is picking up, but quite weak in terms of the signals. On the copper tube monopole, there's also a copper wire monopole in there, and that's the VNA analysis from that. And if you run that, yes, it's picking up something, but it's much weaker. And so that's probably why I was having challenges trying to get signals from multiplying the 2 together, that basically on one of the feeds I'm not getting any signal at all. So
this was the thickness of the probe that's stuck inside?
Yeah, so if I go back to the picture, right, so this one is just a copper wire about 1 millimeter thick, and this one's a copper tube, 1/8 inch diameter.
Wow, and it makes that much difference. Neat.
Yeah.
And can you explain this plastic that's had a better day?
Okay, so this is aluminium, I guess. Yeah, it's aluminium, and it comes when they supply it with a plastic coating on it. And I never bothered taking plastic coating off when I put it together.
Okay, all right.
So it's that's peeling off. So having done that, I decided, okay, get back. Last time we talked about having the 3D printed model but put an aluminium coating on it instead of painting it. Much cheaper way of doing it. It's not particularly easy to do. I used spray glue and then stuck the aluminium to it, but I made the waveguide with a monopole in it, and then I did a test on that, and yes, you're getting signal. And even if I do just the waveguide on its own, I'm actually picking up some signals. They're weak, not surprising, it's only 158 millimeters, but I was seeing something with that. If you then go ahead and put the choke on it as well, and then do the same, you start to see some signals here. Okay, I started to get worried about this blip in the middle. It always seems to appear in my place about 14 megahertz, and so I tried looking at ways of that, but I'll come on to that. But with the choke on there, again, you can see the aluminium coated 3D printed model picks up signals. Probably not as good as the painted one. It's certainly not as robust or handleable as the other one, but it will work. So that's one way you could go as well. So then I tried cleaning up the original horn. This is designed on the Picta radio telescope. So I tried cleaning it up, wire brush, cleaned it all down, reassembled it, and I tried some various things, and I started getting annoyed by this signal here, around about 1414, and I wanted to move it. I wanted to move it further up to 1420, so I got better signal to noise, but couldn't do anything about it. So I tried a 72mm length copper tube, and I pick up something, but it's weaker than before. This is 70mm tube. Again, it's picking up something, but not very much at all. So I then decided, let's try using some different material. So you can buy PLA materials with various powders, metal powders inside them. And this is one which has 5% copper powder inside it. And so, again, there's the waveguide printed with this material. So it already has copper in it. And so when I do the analysis, this is just using the waveguide on its own. It's got quite a reasonable signal, you know, looking in the right place. So I printed 3 of these off. There's a second one, and there's a third one, slightly different in terms of their shapes of the reflection curves. No idea why, but it could be just differences in the copper tubes. But there's one that what I did is, instead of painting it with the copper silver paint, I used a cheaper zinc paint that you use on rust-proofing cars, etc. And just spray painted that with zinc to see if it makes any difference. And there's the zinc one, but again I've got this signal here, and this was frustrating me. And I tried doing a lot of work trying to understand what's going on here, trying to use different size monopoles to shift that peak and get it closer to where I wanted. And in the end I discovered that it's background noise. Because if I do the same analysis at the observatory, well away from my home environment, I get this response. Whereas in my home environment, I get that response. So this is some sort of background signal around where I'm working. It could well be computer screens, but it just shows when you're doing these nano VNA plots, you have to be careful of the environment you're working in, because you'll be picking up signals. So I've moved to doing a lot more out at the observatory, where I've got much better response. And so this is with the zinc painted center, I can get a better response out at the observatory. So I've done a lot of these, and so I plotted all of these out. But what I want you to draw your attention to is that here, the last 4, so I drilled different holes at different heights from the bottom of the tube and placed the same probe in it. And if you put the 50mm probe 50 mils from the bottom, you get this response. You put it 60 mils from the bottom, you get a better response, because nearer 1 is a better on a VWSR plot. You put it at 70, you get atrocious results, but then you go to 80 and you're getting back to signals again, which is almost equivalent to the 50. So I found that very interesting, that the distance from the bottom, where you mount the probe, is as sensitive, if not more sensitive, than the length of the probe itself. And I wasn't aware of that. So that was something new to me. So I've been playing around a bit more with different sizes of hole from the bottom as well as different length probes. And here, just to give you an idea, here's the response from a 50mm hole and a 50mm probe, and there's a 60mm hole and a 60mm probe. And so you can pick up signals in both of them, and the VWSR plots are over here as well. And you can see that, you know, there are slight differences. But this is with the 168mm silver copper painted waveguide and choke. And so, you know, playing around with the placing of the probe is as important as the length of the probe. So then I did some more work and looking at this, and again the interesting ones are here, that if you go from this one here, it's the 168mm waveguide and choke with a 60mm, the monopole in the 60mm hole, but at 42mm, quite bad. 44mm is the best result I've got. 48, 50, 52mm going up gets worse. And then if you take the same one with a 50mm hole and the same probes, you've got poor results. So it's a combination of both the height above the base as well as the length of the probe that gives you the optimum results. But overall, I find the nano VNA VWSR results disappointing. There's you know, a lot of data in here, but the differences I consider are fairly small. But that's my opinion. I also had some issues. Here's even a bigger waveguide, 188mm waveguide with the center only. But in this one, I got the interference signal, and the interference signal was going up and down, doing this zigzag pattern all the way through the results. And so that's why this is so wide, because it's one signal moving backwards and forwards, left and right throughout the entire plot. And so I am having trouble with background noise when I'm trying to measure the results from my 3D printed waveguides. And then this is 3D printed horn with a 160mm diameter waveguide with a choke. It's painted in the copper silver, and this is 50mm hole and 50mm probe. Now, what I'm not really showing you this for any detail here. What I want you to look at is this. This is the response from the amplifier that I've got on here, and so it's giving a result of about background baseline level of about 6,000 units of amplitude on here. And then look at this one, and this is the 3D printed horn from copper PLA. Again, it's got a choke on it. The probe's at 60mm, the monopole's at 52mm in there as well. But look at the amplification here, it's down at 200. Now if I unscrew this, the SMA cable from the feed horn, then the amplification goes way up. But as soon as I screw it back into the feed horn, it comes down here. And I don't understand why the copper PLA is causing such a reduction in amplification on the signal. But that's an observation I've had. Again, that'll be a question. I don't know whether anybody else can answer that. But if you then run the analysis, this is what you get. There is some signal in the middle of here. There are noise peaks, both before and after. There is a tiny bit of signal in here with the copper PLA horn, but not very good. So then I changed the center waveguide for one that's painted with the copper silver, same probes, same hole, and there are some signals in here, again pretty weak. not particularly brilliant. It's got the waveguide on it as well. And then I'm also doing the same one here with the zinc painted one, but I haven't got the results yet. So I've gone back to the 168mm one with the 42mm probe. And if you remember, the 42mm probe was quite bad on VWSR, but it gives quite brilliant signals. So what I've decided to do is ignore the VWSR and just change the length of the probe, keeping the hole the same and everything else the same. So I'm running the 44 one at the moment, and then I will go through the whole series up to 52 to see what difference I get in actual signal recovery rather than worrying about VWSR. And then the final one I've just got here is I did some analysis on all my different amplifiers that I've got, and so some of the amplifiers obviously are defunct. Some of these aren't particularly good either, but it just shows that there's a huge range of different amplifiers you've got. The ones I tend to use are these ones. Oops. I don't know what I did then. Slideshow from current slide. There we go. Are these ones the Despera ones? West Virginia University Radio Astronomy. I don't know what the I stands for, laboratory. But I got the designs from them, and I built a whole series of their amplifiers. They're dual amplifiers with filters in them as well, and so they give pretty good results. But in all my data, the signal, the baseline slopes up from 1418.
Wow, magnificent. So much data and so much analysis and clear presentation. Andrew, I'm very impressed. This is excellent. I'm always interested in the cheap solution so that we can get more people involved. What is it? What were your results for that zinc paint? I'm hoping that's the cheap one.
The zinc paint is running tonight, so I've got that running. I won't get the results till tomorrow. But yeah, I'm hoping that that gives good results as well, because it's a lot cheaper than the copper silver one. But also, if the 20% aluminium, because if you remember that the copper one, PLA with copper, is only 5% copper, and I found that there's a PLA with 20% aluminium in it, and I'm hoping that might work better than the copper one. So you can just do a direct 3D print without having to paint it.
With different 3D printing material, some of them are kind of scratchy and hard, and so you worry about your orifice, and that has to change. What do these metal ones do with that respect?
They're just like plastic, because the copper one has got 95% plastic in it. The aluminium one's 80% plastic. So you wouldn't really notice the difference.
Oh, that's great. Okay.
They're heavier, obviously, because it's more dense material, because it's got the metal powder in it.
I guess. Neat. And there's still hope for just aluminum foil on there?
Aluminium foil works. It's just a paint to put on, and it's not very robust.
Because the weather will beat it up, you're saying?
Yeah, and it's not easy to stick it down evenly across the whole surface, so you get bubbles in it, and just handling and moving it around, it sort of snags and tears.
Yeah, it's awkward in lots of ways. Okay.
Yeah, that's why I'm hoping the aluminium embedded one, just a 3D print of the aluminium, will do it. But I'm just struggling to understand why it is that when you plug the amplifier into the copper PLA one, that you lose amplitude.
And it's not just a resonance somehow. That you're just unlucky with the other dimensions, I'm guessing.
Well, I've got 4 other 3D printed models that, like the aluminium one, is exactly the same dimensions.
Yeah. Okay. I hear you.
So it's not that. It's just, if you undo the SMA cable from the feed horn, you got amplification of several thousand. But as soon as you plug it in, it drops down to a couple of hundred. And I just don't understand why. I tried looking and seeing if there's a short, changed the monopole, didn't make any difference. It's just weird that copper PLA causes that effect. But when you put paint in it, you don't get that effect.
The mysteries of antennas. Wow. Okay. Fantastic. Appreciate all your work.
I was just wondering whether it was due to inductance effects or something like that occurring because you've only got a small proportion of copper in it. I mean, have you in any way been able to measure the resistance across it to see whether it's got a measurable resistance or
I could try that, but I haven't done it yet.
I'll tell you what frightens me about your presentation is that it just demonstrates how very small changes lead to enormous changes in what people achieve. In astrophotography, that's similar, but the astrophotography software has very cleverly got past this with sliders, so you can sit there and just move your slider left and right slightly and say, wow, that works now suddenly. But if you'd like to sit down and try and calculate that exact position, it would probably be virtually impossible. And I'm wondering whether we're in the same position as this in radio astronomy.
Well, I'd love to have a slider that adjusts the position, the height and the length of the monopole.
I've just looked up on ChatGTP, which of course we know is always right. But I'm joking there. But nevertheless, and just ask the question, what height from the bottom do you need to put your monopole? And it suggests it has to be or recommends a quarter of a wavelength. That's a quarter of the wavelength within that particular can, which depends on the diameter of the can.
It depends on the diameter of the signal.
I mean, you understand it better than I do. Let's see what it said.
Because if you think about it, I'm using 100. Well, the design for the waveguide and feed horn from V4MA is 158 millimeters in diameter, but we're looking at a 21 centimeter line. And I always think, well, it's not fitting down the can, but what you've got to remember is that the wavelength is from peak to peak, but it's not coming horizontally across the aperture, it's coming vertically down, and it's the amplitude that determines how wide it is. So you can fit it into the can.
Well, let me just read this to you. I don't understand it, so you can tell me it's a little rubbish, or even maybe you can explain it to me. So, relationship between diameter of the can and the probe distance from the bottom. The feed point, the probe distance from the bottom, should be about delta G over 4. Now, as the diameter increases, the cutoff wavelength delta C increases, since it's proportional to D, the diameter. The ratio delta 0 over delta C decreases, so the denominator, which is the square root of 1 minus delta 0 divided by delta C, all of that little bit squared, increases, and therefore delta G becomes shorter, and so does delta G over 4. So a larger can requires a shorter guide wavelength, leads to a shorter guide wavelength, and the probe needs to be placed closer to the bottom.
Okay. Basically what it's saying is that when you make a waveguide or a feed horn, there's a maximum and a minimum wavelength that it will receive.
Mm-hmm.
And so as you change the diameter, you're changing that maximum and minimum.
Right.
And then what it's saying is that if you change the diameter, you should also change the position of the probe at the bottom as well.
Okay. How big was your can? How wide is your can?
So the standard one that from the VEMA design was 158 millimeters of the waveguide with a 350mm choke outside that. And what I've done is I've also made one 148 millimeters, one 168 millimeters, and one 188 millimeters, just to see what difference the diameter makes.
And what probe height from the bottom did you say was the ideal?
Well, in 168, it's 60 mils from the bottom. And 150, I'm still deciding whether it's 60 or 50. But what I'm going to do is I'm going to do an empirical set where I use a given set of, I'm using 168 one at the moment with a 60 mil hole, and I'm changing all the probes and seeing what actual signals I receive rather than relying on the VNA, nano VNA, to try and decide what's the best, because the nano VNA said the 42 millimeter probe would be crap, but I actually got good signals from it in practice. So I'm doing it empirically with the feed horn to try and see what's going on rather than using the nano VNA.
And forgive me for asking this because I'm sure you've explained it and I missed it, but when you say a 60 mil hole, what exactly?
60 mils from the bottom.
Oh, 60 mil from the bottom, okay. Well, all I can say is that I give up on then ChatGTP, because according to ChatGTP, is it 158 millimeter wide, should be 83 millimeters, so we're way off by about 25%. So, and yet yours is the one that works, so there we are.
I will drill some more holes and I'll put it up to 80 millimeters and see what I get.
Oh, I don't know. There we are. Anyone else? We can't hear you, Heather, because you're muted.
That's better. That makes more sense. So you've gone for some form of I don't know what sort of choke it is that you've used, but the whole point of a Kumar choke is that it changes the feed impedance at the front of the waveguide. Right. And you've put your feed impedance a long way behind. How did you come up with doing that, or was that just convenience of design?
That's the design. If I go back to share again, share screen, and I go, come on. Yeah. So this came from the physics forum.
No, I completely get that, but your design has the front of the waveguide sticking out a long way past the choke, does it not?
Oh, yeah, and the aluminium one, yeah, that's off the Pictet design.
Yeah. So
a different design to this one.
Yeah. Okay. So I just went through the maths quickly, and this one looks right.
Right.
Certainly, if you're making out of copper, this is a fairly standard, accepted set of dimensions. Be very, very interested. Have you simulated this at all?
No, I don't know how to simulate it.
Okay. I might bung it through a simulator because that conforms to the standard measurements. So it may well be interesting to see if we can get a simulation to reflect what you actually saw.
Okay. Out of curiosity, I'm also building a funnel to go on the top of the waveguide rather than using the choke to increase the diameter.
Okay.
No science, just wild ideas.
Okay. Interesting.
Okay, well, thank you very much, Andrew. That was so Sorry.
Can I ask a quick question? It's Mark
Yes.
here.
Go for it.
You mentioned several times Pictor. Is that as in Piraeus in Greece?
Yeah.
Oh, right. Because I'm new to radio astronomy. I started in about February this year. And I came across Pictor, was the first thing I discovered, and I did over 24 hours. You could just fill in a form and submit an observation request, and it spits back an email with some data. And I did it over 24 hours. But I had no idea what I was doing. And now tonight I'm starting to mess around with that data because I understand it a little bit better. But maybe, is Ted still there?
Yeah.
Just to deviate from your subjects about design of antennas, the picture data, it's 2048 channels, and it sends back a list, a CSV file with the frequency in a column, whereas EasyCall is expecting frequency data in rows.
Well, then we need to make a converter, I guess.
Yeah.
A translator
Okay.
is the word I'm using now.
All right, that's what I thought. Okay, sorry, I've got a question though about this Kumar antenna. Yeah, the dimensions, because Alex Pettit promoted making a receiver, a receiver using a sort of cake tin with this loop, a copper loop. And I remember it had to be 23 millimeters from the base of the cake tin. And I think that dimension was quite critical. The cake tin is about 150 millimeters diameter. So, yeah, I understand that the location of your probe is quite critical. But what's the difference between using a loop probe and this sort of pin shape?
Well, a pin, if you had a signal that was directional, I can't remember the right word for it, but had sort of phase to it, you'd be able to pick out that with the probe. But if you have a loop, then it's non-directional, no phase.
Yeah, all right, I understand that. Yeah, okay, thank you.
Okay. Well,
Yeah, no more questions.
brilliant. Well, thank you very much indeed, and thank you very much, Andrew, for that very interesting talk. It's brilliant. Thank you for making that effort to put it together for us. So, moving on to Ted now, if when you've done your talk, Ted, you'd like to see some latest data. While we were doing this, I had up-to-date data from my dish outside processing, so it might or might not be interesting.
Cool. Let me do mine, and we'll slide yours in and talk about that too. All right, I'm trying to share. I'm hoping you're seeing a picture. And I think if I get over here, I can push buttons. Okay, I think there's hope. This is a pre-announcement, I guess. This is not yet quite available because I need to fix it up and clean it up. Otherwise, it'll just cause more trouble. But it looks like we're finding a way to talk to SDRs other than the RTL SDR, such as from NOAALEC and RTLSDR.com. Those are the least expensive SDRs, in my view. But we want to use fancier ones, too. There's the SDR Play, there's the AirSpy, There's the EDIS receivers, like I guess the B210. I don't have these things, so I speak of things I don't know about. But anyway, I got a new program going on here. Easy Call from Ezra is the data collection program. Easy COL for collection. But now I've added an S having to do with SOAPy drivers. SOAPy drivers is an interface above the hardware. There are all these layers, but anyway, in there someplace is a SOAPy layer, and that's supposed to have the same sort of interface for whatever the hardware is down below. And so if I could talk to SOAPy, then I could talk to all kinds of different SDRs. That's the plan. I have a date in here for 2025 and November 1st, and then a letter, and then a letter P, because this one happens to be personalized for SDR Play. I use the P from that word, and we're making progress. This is the first time I've tried to actually make success with SDR Play. I have I think an RSP2, and Andy has a different one. I hooked this up to an antenna that works, and I got signals. It looks great. Andy, this one happens to have that using pins 3 and 4 on the Noelec Sawbird LNA bare bones, and so I'm able to use a reference sample of an internal resistor in the LNA. I turn it on and off. That's why the top of these lines is so flat and looking so consistent, and the real signal's on the bottom, Andy, as it alternates back and forth, up and down in the middle graph. So anyway, we get a spectrum. There's a heck of a spike in the middle. That's really at the center frequency, and that's an artifact of the math in the fast Fourier transform algorithm, I guess, method, and it represents the value of the 0 megahertz component. Well, we call that, instead of AC signal, a DC signal. So that's the value of the DC signal. EasyCom has a way to remove frequencies that annoy us and hide them. And so we have a way to get rid of that spike pretty easily. I'll show you here. But sure enough, I gotta find the button, this one. Over most of a day, I had it pointing straight up, and it found signal in the right kind of places. That's pretty good. Glad to see it actually working. The intensity of the average of each sample is shown here, and on the graph before it started on the right. This one actually starts on the left with increasing time to the right. And sure enough, so this is the galactic plane crossing that is closer to the center of the galaxy, and so it's bigger and stronger. The frequency response, now we look at the bottom, it has a heck of a spike on it. It's got kind of this ripple on the bottom too, which is interesting. That may be an artifact of the way I'm doing it here. It may be an artifact of the SDR Play. I'm not quite sure yet. More experimentation will find out. As I say, EasyCon for analysis is a way to reduce this spike and essentially hide it. When we do that, that spike goes away. You can see it real flat at the top. And everything else gets magnified with the auto scaling in the y-axis direction. So, okay, we see that ripple much more completely here. So it seems to be working. Let me go back to my original screen to have one more point. With these fancier SDRs, we can now have a really big bandwidth. shown on the bottom line here. This is 8 megahertz through an SDR play. I don't think I need to have 8 megahertz to record galactic hydrogen, though. The signal moves around, having to do with the Earth's velocity around the sun, and how it changes every 24 hours because the Earth is rotating once every 24 hours. We're looking at the front of the car, or then we're looking out the back of the car 12 hours later as we drive around the sun. Okay, so that Doppler isn't that grand. Maybe I just want the middle 2 megahertz out of an 8 megahertz bandwidth. More bandwidth is helpful for higher resolution, at least in the frequency domain, so that's a good thing. The SDR works hard, sends down lots of data, so there's a cost to that, but you get much higher resolution in the frequency spectrum. But it doesn't all have to get recorded. So I'm choosing to take only the 1024 frequency channels or frequency bins in the middle of an 8 megahertz bandwidth. That's why it shows only -1 megahertz all the way up to +1 megahertz when centered on 0 at the top. So that seems to be working. To do that, you have 4,000 frequency bins in the readings, and you take lots and lots of readings to make one sample. And then from those 4,000, you start as frequency bin 1536. That's a little bit of simple math. So that you take the next 1,000 frequency bins after that. That's the center of the 8 megahertz. So that's the new thing that's going on now that we have fancy receivers with lots of bandwidth. Andy, you provided this graph from 3 in the morning, it looks like. That's pretty exciting. So it seemed to be working for you. I'm going to have you share your data in just a moment. Although there's strange things. We saw that ripple on the frequency domain, and this is the heat map after I've removed some of that spike and such. And I really don't see the galactic snake that usually curves around, and so I'm a little puzzled by that. Does it go up here, maybe down here? But usually it's much more prominent than this, so that's a puzzle to me. But sure enough, there are 2 galactic crossings. The brighter one is the second one, closer to the galactic center. And then eventually I hope to put all this up on Ezra once I figure out how to install it. I've done so many things. What were the things that were required as opposed to all the strange route that I got here by doing so many other installations. Let me pause now here in case there are any real questions, quick questions here, and then Andy can show us what he has. So this is kind of an advertising for something coming up soon. Okay, Andy, show us what you got.
Okay.
Sorry, I had a question.
Yes, Mark?
Yeah, I thought the resolution depended on the ADC converter, and this AirSpy has got a 12-bit converter, and this cheap Noelec thing's got an 8-bit converter.
Yeah, I'm going to bring up my picture again just because it might be helpful to explain it. We got different dimensions going on here, I think is what's going on. I have to get over here to actually push buttons. Yeah. That has to do with the, let me pull up another graph. How about this one? The 12 bits of the analog to digital converter, the A to D, has to do with your resolution of the strength of the signal, the voltage coming out of the SDR. We quickly convert that into frequency, so it's not even shown here, but the strength of a signal would have to do with a stronger frequency response, or power response. So the 12-bit A to D has the resolution up and down on this graph.
Okay, I've got it. Yeah.
And yet I was also talking about frequency here.
Yeah.
The strength is shown as color. The bright yellow is the brighter power. That has to do with the A to D. But the frequency, I guess, is the up and down part here on this graph. And I think we get to see more detail vertically because we're pulling in so many frequency bins for each reading. Oh, so many dimensions we got going on here. And then independent of all that is time also. So we're up to at least 3 dimensions quickly.
I'll have to think about all this.
Yeah.
Okay,
I
thanks.
can only say it quickly because I've thought about it again and again. It finally burns in. Good luck.
Thank you. Cheers.
Andy.
Okay. Okay, thanks very much. Yeah, so I'll just share my screen. Right. So, before we go on to that, oh, sorry, that was the wrong one. Don't want that one. There it is. So this is over about a 16-hour period of what was coming out of my, was the 150 centimetre dish with the cantenna as a waveguide. The first thing I notice is that the up and down going up to the reference frequency, whereas I normally see those with an RTL SDR on Ezra as reasonably at the same level at the top and the bottom, they do seem to be somewhat all over the place on this. As you can see, we are sort of getting this, rather than peaking up, it seems to be coming down. I'm not quite sure why that is. But that does occur a couple of times in the 24-hour period, so really I'm going to stop there. But that, just to show you, that was what it was. The data that I sent to Ted there. So
I have a response right there. You were showing kind of a dip in the middle of that plot.
Yeah.
Left to right, and that's a puzzle. Usually we have a bump going up. I had to think about that for a while. There's a different frequency response right there. Yeah, it has a valley in the middle of the red dots. That has to do with the reference sample is actually stronger than the signal you're getting from the sky. I guess we're not used to that. This is a different receiver, and it just kind of has a different response, gain response with respect to frequency. I suspect if you had a reference frequency that was less than 1420, that gain to frequency response of the SDR would remain the same, and you get a little hill in the middle instead of a valley in the middle. So maybe that's easier just to have a reference that's lower than 1420 in your case. We're learning about this SDR. I think it acts differently than what we're used to.
But Ted, if you've got an 8 megahertz bandwidth, don't you have to move your reference further away? Because your reference and your spectrum are in the same bandwidth.
I hear you. It makes sense. But if I'm not even, if I trim the bandwidth so that I'm only looking at the center 2 megahertz, all I have to do is move it 2 megahertz, and it's different than what I'm looking at. The reference simply has to be someplace where there is not hydrogen.
But because you're measuring 8 megahertz bandwidth, the hydrogen will be in that signal, in the reference signal, just further down the plot when you're doing your division.
Do you think the hydrogen spreads out that far?
No, because your bandwidth includes if you move it 3 megahertz, you've still got it's still within the window, that you're observing.
But I'm comparing frequency bin of the reference to frequency bin of the antenna. And so I'm thinking only those that if it doesn't contain hydrogen, that particular frequency bin of the 8 megahertz spectrum after the fast Fourier transform and all, that I don't care.
Right.
It could be that we're in a world with such wide bandwidth that's new to me that there actually is an effect far away from 1420 megahertz beyond a megahertz either side, but I haven't seen it quite yet.
Okay.
We have to think about this really slowly because it hurts our heads. Yeah, I understand.
So can't you choose the bandwidth?
Yes.
So plug in, I don't know, bandwidth of 3 megahertz and see what happens.
Yeah, I could put it back to the RTL SDR, which is 2.4 megahertz.
Yeah.
But then why did you buy the expensive box? You know,
I don't know. What's the point?
Well, I'm almost in the position of discovery at this point.
Okay.
I haven't gotten my SDR play to work for radio astronomy before yesterday, so this is exciting.
They're not cheap, are they?
Andrew, help me out. I'm thinking with a larger bandwidth coming in, we can discern, we can recognize a higher resolution in frequency information, right?
Well, the main reason I bought it's got 2 inputs on it, so I'm hoping to use it for interferometry, but
well, I'm actually going after Andrew or Heather on the radio.
Okay, the other Andrew, okay. 2 other Andrews there, what are those come on in?
Yeah, as you increase the bandwidth, you should be increasing signal to noise.
Well, that sounds more like power. I'm more worried about resolution of frequency. You know, more detail along the frequency spectrum.
Well, that's a combination of the number of samples and the bandwidth. Because if you take 2.4 megahertz on an RTL SDR and have a 1K sample size, you're spreading that 2.4 megahertz over 1024 samples. You could then take this higher one and take 8 megahertz, but you're still spreading that over 1024 samples, so the resolution goes down. But if you increase the number of samples across there, then you get greater resolution as well.
Correct. And so I'm doing 8 megahertz and 4096 frequency bins for the readings.
Yeah.
And that gives me the FFT. So then I'm in frequency domain after that, and I've just thrown away the outer frequencies and just don't write them down in the file. That's all.
Yeah.
Okay, good. I think I'm on the right path. Heather, any comments?
That sounds like you're spot on. The SDR Play will also give you, I think it's a 14-bit converter.
Okay, so we even have more resolution.
That's the other win.
The other resolution in the power scale dimension as well. So that's good too. Yeah, you got something for your money, right?
Yeah.
Andrew, what else, please? Pardon me.
It's fine. No, so I think we're all going to have a little badge on or some description on this group to distinguish which Andrew we're talking to. So these are the data sets so far the last couple of days. So so while we were talking here, I put this through the analysis on Ezra just to see what came out, to see if that was in any way an improvement on what Ted had shown a few minutes back, and I haven't had a chance to see it myself, so I have no idea. We'll have a look and see what we got. It just on the off chance that something might be a bit better. Oh, hang on, that's just
EasyCon 81.
EasyCon 81. I haven't run Easy Sky yet, so I find it difficult on this when it is remote.
Okay, so I see 2 days, and I see a galactic snake in purple in there someplace.
Yeah.
What's kind of it? Oh, okay, yeah. I don't know if you treated this as DB data, and so it looks like it's inverted.
I just ran. What have we got? Hang on.
Because this easy call S writes it down as DB. The number's almost. Anyway, it has to be interpreted differently.
Okay. So the one I used was the.
We're getting down to
just that one there. I didn't put any parameters on it.
Oh, okay, yeah, and so it gets inverted. That's fine.
Okay. As easy call.
I
and
have
then,
to think about that to see if that's correct, but for some reason that works out.
And I just used straight easy con. I didn't actually do anything else on it besides that.
Okay. But yeah, okay, you were seeing a galactic snake over 2 days, so the SDR play is talking intelligently. We might be able to improve all this by controlling the game more completely, and so things we've got to do.
So we could just try running Easy Sky, getting that particular plot 200, and seeing what comes out. Is that worth doing, do you think?
Sure. It'll be inverted.
So,
We'll get valleys instead of bumps.
So can I limit it on here to which plot we get?
Yeah, but you're going to have to spell it all out. It's not in my head. That's why I have a help screen.
Blow it. Give up. Just
There's so many commands in the stuff that I wrote, I can't remember them all. And then I keep changing it.
do you know Heather's an expert software writer? Perhaps if you beg her, she might be able to do a GUI for all of this.
Splendid.
There we are. Easy Sky coming up. Just see what we got. So it's still showing a.
That's all right. You need an additional parameter on EasyCon to understand the data in DB instead of power.
Right. But I was just wondering here why we didn't seem to have much of a peak on the other side.
Yeah, still.
That's the thing I don't get.
You're just in a special place in the universe.
Oh well, there we are. Anyway, that's
or the plot's inverted.
but even
Well, up and down is inverted. That's okay. That one I understand. That's a parameter you forgot to put in.
but I don't
But on the
understand
left,
why there
how
isn't
come
on the
it
left.
doesn't recognize the bright galactic plane. Yeah.
Strange.
Is it just at that time of day that you're getting more interference and that's overwhelming the front end of the receiver? That's my best guess.
But it wasn't doing it when I was using RTL SDR and standard
Correct,
Ezra.
but that's a different hardware receiver. This one may respond differently to loud signals outside the band that you're listening to. It may overwhelm the electronics on the front end. That's my guess. I don't know.
Okay. Anyway, that's me just demonstrating the data that related to what you were talking about. Later on, I've got a couple of other little things to talk about, but I'll do that later on. Other people have a chance first. So, is there anything else you'd like to talk about, Ted?
What we're trying to do here is come up with ways to talk to different SDR hardware, and this is a exciting opportunity that we're approaching here. There's some cause for hope. Thanks.
Okay. And we'd like to ask any questions to Ted there? Any more questions or any comments?
Yeah, I've got a question. Well, actually, I think it was Andrew's computer were you running Ubuntu or something?
Yes. Yeah.
Yeah. So, and that's a question for Ted. Is Ubuntu less power hungry than Windows when you run this easy call? Or is that not necessarily so?
The Ezra works on both. Once you get it installed, it works both on Linux and Windows because Python lives in those places. Okay, that's good. It also can run on Raspberry Pi. You say power hungry, that sounds like battery usage, though.
Well, that's because I intend to do observations using only batteries.
Eventually, the right thing would be to put a Raspberry Pi out there, which is like a really small computer, as opposed to a laptop or something.
I did look at this Raspberry Pi 5, and it consumes 25 watts, so it doesn't seem very lean.
But I think the power supply into my laptop is like 200.
I bought this hot swap laptop, and I can run it for 8 hours on one battery.
Cool. Okay, let's use that.
Yeah. But
is it Windows or what? I assume.
It was Windows, yes.
And so it's just a matter of getting the hardware to work through the Windows operating system.
I did reduce the sample rate quite a lot.
Okay, interesting. I'm not sure why you have to reduce. We're talking about the integration quantity there, or what?
Sorry. The sample rate. Sorry, the sample rate went down because I reduced the CPU power. I found I could run it for 8 hours.
And so you have a slower computer.
Yes.
And therefore, it takes longer to count up a big number. Okay. Increase the big number. Make it count longer. The Earth rotates so slowly, we can take our samples. Andy, what was Alex's suggestion? Up to 2 or 3 minutes, right?
Yeah, anything up to 3 or 4, he said. And that's what I'm on a 1 meter dish.
Particularly with our size dishes. With a great big 60-foot dish, we have to think faster.
Yeah.
Yeah, that's all to do with the how much of the sky it covers, and therefore, essentially, just like astrophotography, how much slurring of the stars you get, basically, or how much slurring of that area of sky that you're covering that you get.
I put a default in there for, what is it called? The easy con integration quantity or something like that. Of 31,000, just because that kind of worked nicely and convenient for my testing. That way I didn't have to set it every time. For my testing on these old laptops that folks are throwing out, you can change that, but the number is changeable even on the screen, or on the command line, for just this purpose. Everyone's talking about their faster computers, and they put in big numbers compared to what I had. It's not that Easy Ezra doesn't have parameters you can change.
I know it's got a lot of parameters.
It's called flexibility or options. Some positive word like that.
Just to say that I've got 3 hydrogen line scopes running, and each of them uses an i5 processor with sort of 8 gigabytes of RAM and an SSD of around 250 gigabytes. But they aren't necessarily all the same generation i5, and even ones that are the same generation don't seem to run at exactly the same speed. So the integration quantity, and they're all set to be about 3 minutes plus, something between 3 and 4 minutes. But the actual integration quantity on Ezra or EasyCol varies quite widely. And the only way I was able to find out on each machine how much to use was just to try it and see how long it lasted for, and then alter it, and then try it again and keep going till I had the right length. And the reason I took it up that much was, Ted makes the point that it doesn't matter. You can collect more samples, and then EasyCon, etc., will do the analysis and sort it out, and that's fine. But I was collecting so much data especially when you get to like 1 million samples, that trying to process that was getting ridiculous. And so just collecting less integrated samples means I've got less data to process in EasyCon. That's the reason I did it.
We're back to different choices, different options, different opportunities. Lots of samples or a short time of samples is convenient sometimes so that you can throw them out, or long-term samples are more convenient because you actually get a better result. There's always trade-offs.
A mini PC uses about 12 watts, so it's probably less power consumption than a Raspberry Pi.
Yeah. I think, is it Michelle? You used Raspberry Pi?
Yeah. Yes.
Yeah. And so I was interested in that, going down that route, but when I investigated the power consumption,
I don't have problem because I just plugging. I have a external plug in my garden, so I can just plug in. I have a configuration which is all outside, and I collect the data through the Wi-Fi, internal Wi-Fi. So I don't have any link inside. I don't have to leave open a window. So it's more convenient.
What version of Raspberry Pi were you using for data?
Before.
The number 4. Okay.
that's much lower
very
power
well.
consumption.
It works very well.
Yeah, it's much lower power consumption than Pi 5, from what I read.
At TED, it works very well with your package.
I'm pleased, delighted, and happy. I haven't installed it. I don't think I've installed it yet on a Raspberry Pi.
Yeah,
But you guys have. I think it's great. There's a little trick, and it's kind of documented up in even my README or something that I put in there now.
Yeah, it is a document through your site, so I just use your procedure.
Yeah, there was a special trick for the Raspberry Pi that we had to add, though. Things I got to... my documentation is always out of date. Yeah.
Here's something, Mark, that might interest you. Again, if it's accurate, just asked ChatGPT what the typical power consumptions were. So again, they might not be accurate. But the point that ChatGPT has come back with is that the Raspberry Pi has had a roughly doubling of power consumption in each generation. So if power really is an issue for you, you could go back to Raspberry Pi 3B Plus or even Raspberry Pi 4, which are 4 and 5 watts apparently at moderate load. Remember, you're only using this thing to collect data. The Ezra's really using the underload when it's trying to analyze it afterwards. So for your collection, and if you only got 4 watts, I mean, I have a battery here, just bought off of Amazon for £400 based on solar power batteries, which is just under 2,000 watt hours, so it's 2 kilowatt hours. So if you've got something that's running at 5 watts, that's going to give you what, 20 to 100, 200 hours at 5 watts for 1,000, so about 400 hours that would give you. That would keep you going for a whole week before you had to do anything about the power.
I thought the computer was just more convenient because how do you transfer the data then with from the Raspberry Pi system to someone who processes it?
There is very easy. You have some package software that you can just transfer the data from the Raspberry Pi. You download to your PC. They can give you the package.
Yes, please, I'd be interested.
So you're intending to have it out in your allotment. So I guess if you wanted to stick up a wireless connection, then your power consumption goes up. So you could do a Bluetooth connection on it to your laptop and then just download it when you go there. Alternatively, you could just stick an SD card in the end of it and have it from that.
Yeah,
you can do that also. You can just put a USB. The problem with the Wi-Fi, it can perturbate your antenna, so you have to be careful that I have to mask my. I can show you if you want to share. Can share. Andrew, I can share.
Yeah. Is that okay, Ted? Shall we? Is there anything else you wanted to say, or shall we just move over to Michelle now?
No, not me. No, please. Yeah, go take over.
Okay. Well, let's. You take over then, Michelle. Share about that, and then anything else you'd like to talk about afterwards as well.
I just try, but it doesn't work.
So I hit share, and then I click on Windows and choose my proper window.
There's a share button next door to the leave button at the top right. Have you pressed that?
Yeah.
And the easiest is to and then you have a couple of choices. You can either select the whole screen or you can select an individual screen. I always get confused with the individual screen, so I always select the whole screen.
Okay. Écran entier. Okay. Autorisé. You see?
Yes, it's worked now.
Yeah. Okay.
We see ourselves.
So do you see my the presentation or not?
Yes, it says radio astronomy setup.
Presentation with the pictures on the left.
So you have this is the full screen. Here, Mark.
Looks great.
You see that? So on the right side, I did put it in a watertight, waterproof box, where it's the standard of the electrical distribution, and the Raspberry Pi is inside, and I have Wi-Fi. But I have to put this plastic box, quite far from the antenna. If not, I can have some perturbation.
Yeah.
So, but it works very well. Andrew, if you want, I did prepare something on the meteor detection.
Yes, go.
You want me to share that?
Just ask the rest of the group. Is everybody happy to hear something on meteor detection? I know we're mainly hydrogen line, but sometimes we allow other presentations if it's of interest to the group. Yep. No objections? Yes. In that case, go ahead, please. Yeah. Go ahead.
Okay, so what I am doing is that I use AirSpy Mini with a Yagi antenna. I fix it to everybody know about the radar, the Grave, the French radar, or you are not aware?
Yeah.
The French radar, the Grave, is you can see by the way it comes from the British Radio Astronomy Association. The picture. It's a very nice website. So you can see here there are several antennas, and they track the satellites. In fact, it is the French Air Force that owns this installation. It's close to Dijon, and what you do is you try to follow. You have a transmitter and a receiver, and you try to capture the meteor trail when the meteor travels in the ionosphere. The radar emits on 180 degrees south, and each step is 7.5 degrees. It emits a very strong signal on step of 3.2 seconds. And you can see here, so the interception meteor are detected at around in the ionosphere at around 100 kilometer altitude. And so you can see on the right figure the track where the meteor should be detected. And I am located in Norway, close to Paris, and you can see the direction of my antenna. I did simulate a bit the Yagi symbol. And so I try to detect the meteor, but in fact what is interesting is I wanted to check I received something. And in fact I was very pleased to see that I can detect the reflection of the radar emission when I point my antenna in the right direction. And you can see here, it's very interesting because this was taken in October. And you can see the track of the 3.2 second impulsion of the radar. It's very consistent, but of course, because it shifts sectors like that, I only detect when it is in a section of the full, how you say, full radiation of the radar, the full section of the radar, the 180 degrees, I can capture only part of it. And you can see here on the track that this signal appears and then after a while it disappears. And when there is a meteor, then I get a rather strong spike like that on the right. Here is a more, you can see the signal, the regular signal of the radar. There is a software package called HROF, which shows developed by a Japanese. I did try to use it, but I have not been so far very successful with it. What you can see also is interesting is sometimes you can detect this track here. And this is, I'm not sure if it is a plane or a satellite that passes through the radar signal. But it's and this is more detection of meteor that I did last year. Okay, that's it. Any question?
Thank you. That's fun to see. What was the name of the Japanese program you were going?
HROF. I can put that.
Ashcroft. Okay.
HROF. I can.
Be fun to explore that as well. Thanks.
I can send it to you.
Good. Okay. You're still sharing.
Yeah. Let me check if I can find it.
So that Ashcroft software,
yeah.
is that the one that you're using to produce the waterfall graph?
No, the waterfall I use SDR++.
Oh, right.
HROF give you, let me see if I can find it.
We're seeing all this. Maybe you want to stop sharing.
No, it's okay. No.
I think it's fun to see something that looks so familiar, but it's in French.
So you see here, you normally receive a signal, and then it will detect some. So here, I think it just receives the signal of my because it's linked to my the output of my loudspeaker of my PC. So you see some signal, but normally you see on the graph on the left you have the signal when you have a meteor, and you would see a signal, and it's recorded every 10 minutes shift, and it registers the data, so you can make what they call a colorgram, which is a graph that gives you day by day, hour by hour, the number of meteors that was detected.
So we're seeing your voice being recorded here.
Yes.
Will you clap your hands for us? And that'll make a louder response.
Then I have a meteor.
Yep.
Here I have a meteor.
Yeah, make your own meteors, exactly.
So but I have some problem to make it work, so I don't know. So, but just what is interesting in after you can get a colorgram, which is I think it's this one. That will collect all your data and build a graph. It will build a graph with hours, you see on vertical hours and days. And so you have a nice graph, and when you have the Perseid or some really strong meteor shower, you can see very well that it comes from, you can see the hours and the days of the shower. Okay, that was a presentation on Blue.
Yeah, that's wonderful. Thank you very much, Michelle. Has anybody else like to make any comments on this?
I took notes.
Just for comparison, I'll just compare with something. So I'm just pulling up my meteor observing setup, which also uses Graves. So I got Spectrum Lab going here,
okay.
which is on a 3D plot.
Mm-hmm.
And this, I don't know how is it HTFFT, was it? I don't know how that actually decides whether it's found a meteor. This one's got a conditional action script which it runs, which then records the meteors and records a screenshot, and also records a sound as well. All sounds very good. Not sure how good it really is, but it sounds like it. And you were talking about colorgrams, so for some reason cologram keeps crashing out on me. I don't know why.
So you use the same, colorgrams.
Yeah, because you can do. Do you put yours on RMOB, Radiometer Observing Bulletin?
Not yet, because I didn't have really interesting data to share.
Yeah. So anyway, this is since the beginning of the month. You can see our meteors coming through. So we have a reasonably high rate in the mornings at the moment.
Mm-hmm.
So we're obviously in the midst. That tells us of a shower. I should better tell you which shower. Which one are we on at the moment? There's one coming up to peak, isn't there?
I don't know. So right now, I don't know.
Anyway, well, thank you very much then, Michelle. Brilliant, thank you. So who have we got next? So, Mark, you've asked lots of questions. Is there anything else you would like to show us or talk to us about this evening?
Oh, I've got nothing to show you really, sorry.
I'm just thinking you were showing stuff yesterday at SARA. I was wondering whether you fancied showing any of those slides again tonight.
Not really.
Okay. Fair enough. Well, that's.
I'm hungry. I want to go and eat.
Oh, well, that's okay too. That's fine too. Okay, who we got next? So Heather, are had a very interesting chat with yourself about meteors not so long ago, about the BAA beacon, which was quite exciting, and I hadn't realised you'd programmed all of that stuff. So,
excuse me. We did say last week I'd do a presentation for you on it, but maybe we'll save that for another day. Yeah, it's all good stuff, isn't it? These meteor stuff.
Mm-hmm.
Yeah.
Well, is there anything related to hydrogen line that you would like to talk to us about today?
Not really. I mean, I have a question. I'm at the point where I'm thinking of actually setting up a dish. What's the general starting point? Where should I point it?
Well, I think Ted's the best person to answer this question. Anywhere, isn't it, Ted, really?
You point
South.
it towards the equator and at about 45 degrees up from the so if you're in the northern hemisphere, point it to the south and 45 degrees up from the horizon.
Perfect.
Okay. Can I suggest something?
Yeah.
Do you know Stellarium? Heather, do you know the programs? So you can see where the Milky Way is. That's perfect.
Yeah.
Yeah.
Okay.
Brilliant.
I have one point. We were talking about what meteor things are coming up, and this is a picture of some last night's meteor detection with these cameras. But on the bottom, can you see my cursor down here? I'm not sure. We can see all apparently there are 88 meteor showers, and this kind of is a calendar with the red line where we are in the beginning of November. So yes, indeed, we have a whole bunch of meteor showers that are going on right now. It's a handy chart.
Oh.
My impression is the Geminids is almost half of them up here, and the Perseids over here is about the other half.
Yep.
Okay.
But good reasons then for us to be
testing
testing at the moment.
Now.
Yeah. Fantastic. Thank you, Ted.
That's a very nice chart.
So the Global Meteor Detection Network.
Okay.
Yeah.
Global Meteor Network.
Global Meteor Network.
GMN.
Okay. So sorry, Heather, what were you talking about a second ago?
No, that was it. I said my bit. But if a good starting point is going to be south and 45 degrees, then that's what I'll do.
Yeah. Well, one of the neat things about Ted's Ezra is you don't have to be exactly south. But you can plug in what you've got exactly, and then once the 45 degrees is good because that maximises you missing your neighbour's trees or house or whatever, and giving you a good signal. But at the same, and particularly from the UK, if you go up towards the zenith, you often don't hit the Milky Way unless you're in the middle of the summer. So or I suppose in the middle of the morning, sort of early hours of the morning, you start picking it up, I guess. So it maximises your chance of picking something up quite quickly. That's what I would say. But with TED software, you do a drift scan at a particular elevation, and then you come back a few days later and you change that slightly. Then you change it a bit more. Then you change it a bit more, and you do these repeated drift scans, and that's when it starts mapping things out, and things get very exciting.
If you want, I can show you one example of.
Michelle got lots of data.
Yeah. But I didn't work. I'm not in my house right now, so I could not make it. But if you want, I can just show. Where is my partager? Sélectionner une fenêtre, un écran entier.
So while you're finding that, Ted, can I ask you a question then related to that? You were saying pointing south at 45 degrees. So from your perspective, what difference does it make if your dish is pointing significantly far away from south? Does that make a big difference to the quality of the signal you detect?
If you point too close to the north or south pole of the Earth, then you won't see the galactic plane go by. And so I try to get you at least pointing towards the equator, wherever you are on the Earth, so that at least you're kind of getting some galactic crossings each day.
You can,
for Michelle, it's kind of lower green stripes there.
Yes, all these lines are one scan. So here you can see about how many? 91 scan from minus 15 degrees to 110. No, 15 degrees to 100. No, I cannot see. It's minus 15 to 115 elevation. And you oriented south. At least when you scan, you need to keep always the same orientation. And then you elevate your antenna from minimum as you can go, because you have obstacle houses, etc., to 90 degrees, even more. And then what happens is that you scan the galactic plane. H-line is is a crossing, and you can see the dots here. So if you start at 45, you will get just one line here, but you need a lot of line to constitute the full map. Like you can see here the arms of the galactic arms. So you need to collect a lot of data. But if you start at 45, it's rather good because you don't have any obstacles.
Okay, thank
How
you.
did you achieve minus 15? Are you on top of a hill?
No, it's because it's not minus 15 from the, it's a mistake. It's not minus, it's 15 to 115. 115 is when you oriented north. It's 15 to, sorry, it's a mistake. 15 to 115, and 115 is because I oriented the antenna north. So from 90 to 115, it was oriented north, and from 90 to plus 15, it was oriented south. I could not go lower than 15 because after I had trees and houses that mask the sky.
So if it's greater than 90, you're bending over backwards.
Yeah.
That's the outcome.
I tried doing that and my kit nearly fell over, so I didn't do it any further.
If you use something like Mark says, Stellarium, and you look at the line of the Milky Way as it progresses through the day, you'll find that when it gets to south, it's more vertical than it is either in the morning or in the evening. And so that helps you when you point south. You've got more definition, if you like. If you were pointing at more east or west, then you're going to get lower horizon for the Milky Way.
Okay, yeah, that's an interesting way of thinking of it. Yeah, thank you for that. I hadn't thought of it that way before. Oh, very good. Okay, well, thank you very much, Michelle, for that. That's really helpful. Thank you. Okay, so moving on then, Andrew Strong. I have to give everyone their surnames so we know who we're talking to. Are you still there, Andrew? Or has he left? Okay, perhaps John.
Yeah, no, I'm still here listening.
All right, would you...
I haven't made any progress. I've actually ordered some time ago the antenna, but it seems to have never arrived. There's a problem with that was a scope in the box. That's how I got into this.
All right.
But it never arrived. I think it's in the customs or something. I don't know.
which antenna have you organised? Have you
That
ordered?
was the scope in the box, I think, which I saw. And so I'm still doing my hand radio stuff, but I'm only doing optical astronomy now. But I like to try and make some progress on this.
But you're based in the UK, aren't you?
No, I'm based in Munich.
Munich, of course you are. Forgive me.
Yeah.
I'm just wondering how. So you've ordered directly from the States the scope in the box package.
I did actually, yeah, one time, but nothing ever happened. I think I paid for it even $200 or $100, and nothing. I don't know. I don't know how I should follow up. What should I do? I mean, I'm willing to pay for another one.
No, I think you should contact them, because when I also started off on this stuff with scope in the box, and
Yeah.
when I contacted them, I was told that you couldn't order outside the US. So what they did was they sent me a parts list.
Oh, yes, that was it. And then you sent me all the details of how to get the parts.
Yeah. So
Right. Anyway,
so
I didn't do anything after.
Yeah, I think you should contact Scope in the Box.
Okay.
Get the order cancelled, your money refunded if you paid for it, and then just buy your parts locally.
Okay. Good going on.
I mean, they're really not difficult to put together. If you're worried that it's somehow you're taking on a big project by doing that, those parts that all the Scope in the Box package in the States does is they've just put a parts list together from Amazon and directly send it out from Amazon. So it's no different to if you went on yourself and just bought them.
So remind me, so you get the antenna and all the back end stuff. I wasn't quite sure whether that's part of the deal or.
Yeah, one possible reason why you've not received it is if they have agreed to send it out to you from the States, is that there's no Newelec Sawbird retail versions available on the H1s. So they're waiting for back orders on that from Newelec.
Okay.
You can get a bare bones version, but you have to contact Newelec directly. It's not available on their website or on any other site. You have to email them if you want the bare bones. That's the one without a case on it. And you can do alternatives. But if you're waiting for the Newelec one, it's going to be another month or two before they get enough in back from China.
Okay.
That's the one with the plastic case.
I'll get that.
Just say that Ted was. You might not have been aware what Ted was talking about at the beginning, but when he was talking about crossing two pins in the Newelec, on the Newelec Sawbird Hydrogen Line version, in the bare bones, but not in the retail black box version. I say retail because that's what Sawbird itself call them, the retail version. There are two pins that if you link those two pins together on the little board that's in there, it actually sends the signal through an internal 50 ohm resistor rather than getting a signal from the aerial. So therefore, if you use your own external bit of kit to switch to open and close those two pins, you can use it to sorry, Ted, what was the term you said I should use? I said calibration, didn't I? You said it was the wrong term to use. What term?
Reference.
Reference sample, sorry. You can get your reference sample using that 50 ohm resistor, but at the end of your coax cable and after your LNA, so you actually get a better reference signal than if you've got one that's down near your SDR. You're going to show us, are you, Ted?
Well, I'm trying to. It works for me. The bare bones, you could spark it, I suppose, with your static electricity with your finger, but I like it just because I can get access to this 4-pin connector here.
Mm-hmm.
And it has a built-in reference of like a 50 ohm resistor. I'm not sure it's 50 ohms or anything else, but it's constant, and that's what matters to me. That's all described on the Ezra web pages in those PDFs. It's number hardware 2. Anyway, but this may be the older version of it. I just don't know. But apparently, Andy, you have to email them directly to get this somehow?
Yes, yeah, at the moment. They're the only ones that actually are available, but you have to email New Elect Direct if you want to get them.
I wonder if I think that's true. Oh, I can't get there from here. Let's try this. All this stuff is in the way, and I can't push the button behind it. There we go. I did a search, and I don't know. These guys say they sell it to me.
Oh, they've got some.
So,
okay.
Look for the phrase over here: Noelec, Sawbird, plus H1 bare bones, and maybe someone else has them, or maybe they don't have them in stock. So yeah, I don't know.
All right.
But that's the weird thing. It doesn't come with a case. Bare bones.
Yeah. Does it have an LED on it?
Oh yeah.
I do like the LEDs because that way you can look out your window and see whether you've remembered to turn your bias T on.
Yeah, I go out at night and say, yep, the light's on, that's a good sign. The voltage is okay. I don't have to up the voltage.
When you're an idiot like me, you need things like that to give you some feedback. Otherwise, you'll go a week later and find none of it's worked. We did it yesterday, weren't we? We were talking after Sarah had... somebody mentioned, did I turn my LNA on? We were looking at my data from your...
Yeah, is the cable connected? Is the light on? All these things are important. You'll find out eventually.
I couldn't even remember whether I'd powered up the LNA when I'd done it, so I had to go out and check. It's ludicrous. Anyway, so that's what I suggest, Andrew, that you contact them and find out what the situation is, because it might be that they're just waiting for the LNAs to come in, in which case you might be happy to carry on waiting, or alternatively you might prefer to cancel it. But bear in mind, if they are waiting for the LNAs and they're still going to send it to you and you do cancel it, you've still got the question of what you do about an LNA in the short term.
Okay, I'll still. One other thing I could mention, since I wanted to do astronomy during the day as well as at night, I got myself this is quite different, an H-alpha camera, so you can photograph the solar, look at the solar prominences.
All right.
And that's really amazing. I'm really enjoying doing that.
Wonderful, wonderful. Are you getting some nice views?
Yeah, it's incredible. It's called Akuta, is the name of the scope.
Got somebody in my club sport one, a little green thing, isn't it?
Yeah, it's pretty amazing. I mean, it has an incredibly, really, the bandwidth for H-alpha is really small, so it really picks things up. And you can see you can see the surface of the sun, not so well though, but you really see the prominences. So that's something else. That brings me. What about doing radio astronomy of the sun? Do you guys do that?
Well, we were talking about this in the SARA group yesterday, and there's certainly at the moment there are people who are trying to, as just fun projects to do, and what I might well do next is actually checking polarization of the sun. Yes?
Can I interrupt?
Yeah.
I had a question, probably Ted would be able to answer. I was interested in this solar astronomy, and there's something called SuperSID from Stanford University. Does that still exist?
Yeah. SuperSID is actually, the hardware is provided by Sarah. I guess you make a request and they send you one, essentially. Mm-hmm. So look at the Society of Amateur Radio Astronomy website. What it does, and it isn't much, it's a little audio frequency amplifier is all it really is. You connect it up to a great big coil of wire. What is it, 600 turns, maybe a meter across or so. It hardly matters what the shape is, but you are receiving very low frequencies. We often talk about megahertz, but this is like down at, is it 50 kilohertz? It's pretty low frequency.
About 20.
20, okay, even lower. I haven't done it yet, but I've seen. And what we're doing is listening to a transmission to submarines. It might be from the center of the U.S., for example. I'm sure other submarines get talked to at this very low frequency. Of course, they're talking in code. We don't know what they're saying, but their radio signal is influenced by the path through the ionosphere. And the ionosphere is affected by the solar radiation and things like that. And so indirectly, you are studying the sun's influence on Earth. SIDS. Does that help, Mark?
Yes, I did read about it. I know this software from Stanford, it uploads data regularly, doesn't it?
Or Stanford had a flood, and so their computer room got swamped, and I don't think they've ever recovered. So I'm not sure if Stanford is actively involved. But there's the picture. Andy, tell us all about it.
Oh, yeah, just to supplement what you were talking about. So that's the Super SID on the right-hand side, which is you can actually do this without having a Super SID, apparently. But it provides both isolation and a bit of amplification. On the left-hand side is somebody's version of one of these VLF aerials there, and about 150 meters or so of cable wrapped around across. You can make them quite small, so you can do them inside your house. I've got one, I'm looking at it at the moment on the wall, or hanging off my bookcase. So you get that, and then in terms of options, you've got two. So mentioned the Super SID one, so there's your price for the Super SID, really quite cheap. Which you're talking about the actual Super SID itself isn't interestingly on there. That's weird. I thought it was on there. There's just the extra bits. Okay, I think you're talking about like $100, $150, and then maybe a bit cheaper, maybe $75. But the thing, and then there's a power supply, and you need a computer that's got a reasonable sample rate, 96 kilohertz. Now anything modern will do that, but you can use for this project, you can use some really old XP Windows machines if you want to, and some of those don't have a big enough sound card, so you might need a new one. And then some antenna wire, which you can just buy from Amazon, and a bit of coax cable. It says 9 meters. You don't need 9 meters. It's just however long it is from your bit to your, to your receiver and your computer. But again, $100, $150, or £150, you can do this. The English version. The UK Radio Astronomy Association have their own one. You can see the prices are a bit higher on this, partly because we're in the UK, but also because it's probably a better put together piece of kit. But there is a trade-off. So this actually is a proper receiver. It's not just an amplifier, and it's tunable receiver. So so as a result of that, you tune it to a single frequency. The best frequency in the UK is 23.4 kilohertz. So you can tune that to that, and therefore potentially get a better signal, because it's specifically trained, especially if you use it in conjunction with their aerial tuning unit at the bottom. But again, the price is starting to get a bit higher. And they sell an aerial kit. There's no real reason why you can't make that aerial yourself in the same way as the Super SID one. You don't necessarily need all these posh bits of pre-cut wood. So you could do it a lot cheaper than that. But the little aerial looks very nice if you want something inside the house, just to say. So that's the English version, and then the American version. So the English version gives you potentially a better signal, but only on one frequency. The American version, one of the advantages of the Super SID is it may not give you specific frequency amplification, but what it does do is pick up a range of signals pretty much all the way from 0 hertz up to about 25 kilohertz, anything that your sound card will take. And so therefore potentially you can pick up multiple VLF transmitters and triangulate your signals, which is quite fun.
If you just point your normal hydrogen line antenna at the sun, you will pick up signals as well, because that's what I did for demonstrating interferometry.
It's amazing how many things you can do. The super SID, the SIDs work really well. Meteors work really well. Hydrogen line's a bit more difficult, I would say, but worth persevering at. It's nice to have something that works. Sorry, Heather, you can say something?
Yeah, have you looked at the water maser stuff?
Me? I've got, well, for hydroxyl masers, I've got the kit in the garage. There's a guy called Eduard Moll, who's, I think he's in Germany, he's on SARA, and he does it with a 1 meter dish and a HEQ Pro mount, and does amazing things with those. So it all depended on buying a particular low noise block, 20 gigahertz low noise block, and I managed to pick one up second hand from the American eBay site, and he knows that if you can open that up, there's a little tunable screw and you can tune it right up to 22 gigahertz. So I've got the kit. I just need to get around to doing it. Ah, that's yours.
I just got given it. It's it's a tunable low noise 22.3 gig receiver. So
Wow.
yeah, that's the next project.
How heavy is that? Looks like you need a decent dish to hold it.
5 kilos.
Oh gosh. Anyway, be interested to hear about that when you get it going. Yeah. Anyway, does that answer your question there, Mark?
I think the sound card's a bit of a problem because aren't they 48 kilohertz?
Well, I think you might be able to run it on a 48 kilohertz one. The best thing is if you go on to the Super SID website, Stanford, you can download their manual, or if you can't get it from there, just let me know and I'll send it to you, and you can just read what specifications are. That would be best. I think it may well work on a 48 kilohertz one as well. Just get a bit more resolution with the 96 kilohertz.
Okay, thank you.
It's after all VLF. It's not as if we're trying to pick up microwave signals here. Okay, so moving on to John. Hello, John. What would you like to talk about?
Sorry I was late on parade. I was at the opticians. But, I think I can see you now.
How many fingers am I holding up?
Yeah, well, you did all that nonsense with me. Full battery of everything, testing everything. But yeah, I mean, KA band stuff. Bit tricky perhaps, but there are KA band LMBs out there. 20 gigahertz type stuff, but that's probably not beginners level bits and pieces really. That's perhaps getting a bit more advanced, but I've seen some good results. Well, we both saw them at the Rutherford Appleton Labs meeting that we went to.
Yeah.
That was that was really good. So yeah, I'm glad we were able to get to that. But I haven't really been doing anything much in the radio astronomy field since we last met. Just gathering stuff as eBay keeps providing little packages keep arriving in the post, you see. Bias tees and things. Just mounting it on a board so it doesn't get molested. So yeah, doing little bits, but nothing actually substantial happening quite yet.
Well, my wife's decided to have a talk to me today, and it's about
I get those all the time.
It's about the number of parcels that have been arriving in the post.
Yeah.
So the instruction has been there should be no more of said parcels going through.
The postman keeps bringing them. Yes.
I know. So it sounds like it might actually be at marriage breakup level if I don't stop it.
She called me in the garden the other day with a 100-foot long tape measure and a clinometer, trying to work out angles I could put the base for a 4.5 meter dish, and that was making her very nervous. I I was trying to work
Garden
out.
beautification project.
Absolutely. I was trying to work out which trees I need to take a chainsaw to, because that's the first tool in the antenna maintenance toolkit is a chainsaw. It's never the antenna that needs adjusting; it's the surroundings.
The environment. Oh dear.
So that brings me on to the speaker at the next meeting, who is a solicitor, who is going to talk to us about how to deal with divorce and make sure you walk away with your telescopes.
I won't be walking with this one. Forget it.
There you are, Mark. You need a 4.5 metre dish. That's why you've got problems with your
Go big.
action line.
Go big and go. It's
meters.
the only way. It's the only way.
Yeah, at least 4.5 metres. 10 is probably better, as Ted will tell you.
Entry level, yeah, entry level stuff.
Entry level, yeah.
Now, a lot can be done on smaller kit as well, though. Yeah. Whereabouts are you, Mark?
I'm in near Stockport.
Okay, not a million miles away, really.
No.
So Heather and I are not far apart, about 10 minutes, in the depths of Shropshire,
Oh, right.
not far from a train station at Church Stretton.
I know. Is it Kirk Castle? Is that Shropshire?
Yeah, just over the border or on the border. Yes, that's not far away.
Yeah. Okay. Yeah.
So
Right.
not far from us, really. But we do. Oh, it's not so much astronomy, but more microwaves. We have a little microwave day and an Earth, Moon, Earth bounce day here coming up in a couple of weeks, which should be a lot of fun.
Okay.
You should take your new LNB along to that, Heather, I think.
Well, I think Heather's frozen on us.
She's frozen on us, yeah. Are you still there, Heather, or have you left us?
I'm
I think she's broken.
still there. I don't know. Can you hear me?
Yeah, but
Yeah.
just about here. Yeah, your video's frozen at the moment. Yeah, Heather will be with us. So whether you could join us on that weekend, Andrew, I don't know.
I think it's probably not going to be possible. I think we're going away as a family that weekend, but I did appreciate the invite.
To
Thanks.
Shropshire.
To Shropshire, yeah. 2 weeks' time, did you say?
The 22nd, 23rd of November.
I will double check it to make sure.
So, more microwave talk on the Saturday and Earth, Moon, Earth on the Sunday.
See, that interests me. See, 22nd and 23rd of November.
Yep,
Yeah.
correct.
Yeah. Okay. So in that case, I think I do have something I'd like to show you all before we finish. So, some of you will know Brian Coleman. Heather in particular knows him, and I'm sure you do, John, as well.
Yeah, you know him very well.
And John likes making things. So, he made a couple of these a few years ago, and gave one away, and I've been given that one. So, welcome to my new 3D printed feed. It's not quite 3D printed, it's aluminium. So, apparently it's quite good. But it's also a bit similar to sort of Heather's, I don't think it's quite 5 kilograms, but it does make me wonder whether the 8-petal solar cooker dish will carry that. So in fact somebody's giving me a 2-metre dish tomorrow, which is a solid thing. It's on Wednesday. It's a solid thing. I've got to drive up to Leicester and pick it up and bring it back in my trailer. So that's going to be my next upgrade.
Mind it doesn't get bounced and distorted.
What, in the trailer?
Yes. How wide's your trailer? Probably not 2 metres wide.
It's not 2 metres wide, no.
The safest way to either make an A-frame to strap it to,
Uh-huh.
or lie it face down
Mm-hmm.
on some supporting timbers across the trailer, which will make you a 2 metre wide load, but that's perfectly legal.
Okay. I'll see
But
if I can.
you may want to make sure you've got trailer lights that are the width of the trailer. You're allowed an overhang beyond lights of 12 inches legally before the police get excited about you.
Right. Okay.
I know this from moving 3-metre dishes down the road.
Mm-hmm.
And a 3-metre dish, no matter how you lie it down, is going to be more than a wide load.
We as a club a few years back, were given a dome. And a number of us went up to Yorkshire to pick this thing up, complete with flatbed trucks and the works, and that had extra bits sticking out the back of it to warn people of wide load and all that sort of stuff.
You're allowed quite a long rear overhang, but you're not. It's the side overhang is they get particularly excited about.
Right. Yeah. So, sorry about that. That was my phone. I'm switching it off. I should have done beforehand. My apologies. Yeah. Well, thanks for that advice. I will see what I can do tomorrow. Yeah.
I look forward to seeing what you managed to accomplish with this. It'll be good.
Probably nothing very much is the answer, but it's great fun trying in the first place.
Oh yeah.
Yeah. So I think it was Mark earlier on that asked the question, "What's the point in getting things like an SDR play device and all that?" And they're probably, in reality, you can do so much with a simple RTL SDR and something very
everywhere.
Yeah, exactly. But you can do so much with these things, and unless you're going to really start doing some research grade stuff, it probably isn't worth that much changing everything.
But it's got friends. And FunCube dongles and.
Yeah, have you seen the price of a FunCube dongle at the moment?
No.
It's about £170.
They're much better filtered than any of the other USB dongly ones.
Are they?
I don't know if they're worth that much. But some of the money does go to AMSAT UK.
All right.
So,
There we are.
yeah.
Okay. One last thing I wanted to show you all, and then I'm done. Here we are, the screen. I'm sure everybody's probably getting a little bit tired by now. Oh dear. I seem to have so many things open. Right, so I know everyone here is aware that I wanted to have a go at using 2 orthogonal monopoles, and I know Michelle earlier on was talking about that, so I just put this in to show what that meant, but he's already shown us a picture of a better waveguide with his monopoles, and this is mine. I'm now aware that maybe I need to change these over to some 1/8 copper tubing, given some of those previous results. Sorry, it was Andrew, wasn't it? Not Michelle. Andrew that gave us those results. This, if you wonder what the wire is between the 2 sides, we were talking about using a phasing wire to try and combine the 2 together, but there were concerns expressed during a SARA meeting, so I disconnected that, and I've done it on 2 separate machines rather than having them joined like that. 2 separate computers, 2 separate SDRs, 2 separate Neuralink Sawbirds, and then combine the data afterwards, or at least demonstrate the data afterwards. And this is the last slide, and that's just to show that, not surprisingly, as we know that overall there isn't any detectable polarization of the Milky Way at the sort of kit we're using, but nevertheless it's nice to have demonstrated it myself, that you can see that the 2 traces are pretty much exactly the same on the power traces. And this also shows, as an aside, why I was concerned about what's coming through on the SDR play, because you can see here that this is just with an RTL SDR dongle, and that we're getting some nice peaks on both sides, but on the SDR play for some reason we've only got a small peak on one side. Anyway, there we are. Thank you. That's me done. Is there anybody who would like to say anything else before
Did you want to deal with Paul Hearn's question?
Oh, yes, thank you for reminding me. So Paul couldn't make it this evening, but he has sent us a question, which is, what cable would the group recommend for a signal line from the LNA to the SDR for H-Line, and he's looking for about a 15-metre span.
I would recommend putting the thing right next to the Sawbird and using a USB cable or a network cable.
You're muted, John.
Yeah, exactly that. Catch 5.
Okay.
Or better.
Okay. Any other suggestions?
But mount the computer behind the dish and doubly screen it and ferrite all the cables in and out. Otherwise, you'll be creating more noise locally than that'd be useful.
I'm going to make an alternative suggestion, which is from my own experience and also my conclusions from discussions on SARA, which is that, firstly, to say that I started off having the LNA next door to the SDR, which was next door to the computer, all of which was not next door to the dish. So it was dish, coax for some distance, not so much of a distance, less than 5 meters, and then usually with a 5 meter coax actually, and then into a box that was located a little while away to try and reduce interference, that had all these things in it. And I discovered that even using LMR 400, or at least actually SMR 400, which is KMR 400, which is a Chinese rip-off of LMR 400 cable, i.e. very high performance cable, I still had significant attenuation down that 5 meters. So that was quite an issue, and a number of people on the SARA forum had suggested not that everything needed to be next to the dish, but that the LNA needed to be next to the dish. So if you look at what's in a newer LEC, essentially the suggestion is that even a small run of coax a very even high quality coax, if you look it up, can lead to about a 2 decibel loss across that length of coax. So 2 decibel equates to about 50% of your signal. So that's the problem. You can lose 50% of your signal by sticking everything down a bit of coax before you even get to the LNA. So these newer LEC LNAs have 3 components in them. They firstly, any filtering has some loss, insertion loss in it as well. So you gain losing signal. So what the newer LEC does, it just has an amplifier to start, which amplifies the signal before it does anything else, a small amount of amplification. And then that compensates for the loss that you get on the filter, the SAW filter that comes next, so that we're not overall not getting loss. And then the next amplifier amplifies the signal so that when you go down the cable, the loss that you get is already compensated for. So you should end up without too much of a problem at the end. The only problem is that I again made this mistake. It's the real rookie's mistake of using RG58 cable. And I hope you're not using RG58 cable, Mark, because it's a nightmare if you are.
No,
it's not rated. It's not rated for 1420, and anybody with radio ham friends will be getting RG58, and it's just not rated at this level, and therefore you just lose too much on it. But repeatedly, people on the SARA forum have been saying that RG6 is fine. So RG6 is your ultra cheap satellite cable. It's not, it's a bit fragile, but it'll do the trick as long as you amplify it before you send it down it.
It's coming through here. The thing is, it's got a foil wrap and a solid centre, and it is designed to carry the LMB signal from your satellite LMB to your set-top box. So it is designed to operate around about 1 gig to 2 gigs tops. But really, if you need to get it either hardline, little SMA connectors and some hardline. If you are going to separate the feed from an amplifier and filter stage at the feed point, if you can put them in line back to back, so you're not casting a bigger shadow on the dish, that's also quite important. And just basically get as much amplification and filtering done right up at the feed point.
Yeah, that's what I do.
And as that new elect does, it amplifies, filters, and then amplifies again. The first amplifier is probably about 20 dB or so filter, and then probably a 40 dB line driver amp behind it. They're quite powerful, the second stage amps, and that'll push it down a reasonable length of coax. And then really you want to be dropping it out from its 1400 megs pretty as close as you can to the behind the dish now, and either straight into a Raspberry Pi through the dongle, or drop it to another IF if you must have all the RFE bits back in the house or somewhere. Try and drop it to another IF to bring the signal back on, so you've got less loss. Different ways of doing it. But if you can get it into a Raspberry Pi and bring it back on some quality network cable, that's the way to do it. But you don't want any computey bits forward of the dish, because you're going to be generating an awful lot of RF noise. If that makes sense to you guys. Double screen it. And ferrite the hell out of the cables in and out, so you're not radiating off the power cables or any randomness coming off the coax itself. But coax cables are not all created equal. Some of this stuff is got minimal braiding and is very, very leaky as a coax, which also leaks inwards as well as outwards. Whereas actually the cheap satellite cable, the RG8 stuff, with its foil wrap, is actually quite good for that.
Oh, did I get it wrong? Is it RG8, not RG6?
Is it RG8? Or is it RG6? I might be wrong, but yeah, I think you're right. Is it RG6? Standard satellite TV cable.
Yeah.
And then you can get simple F-type. I've got one here somewhere. F-type to. Is it probably already on? No, it's not already on the receiver. Been creating all sorts of stuff. Oh, it's on the bias T already. So this is for. So you can see it in this light. There's a cheap bias T cable tied across a circuit board with a little power light and then 12 volts in. This is for powering an LNB, not a new elec system. So this is for actually having geostationary satellite comms for an air cadet squadron. Another hobby. Yes. But those are cheap. They're about £4, I think, off eBay. The bias T component on the end of this.
Have you noticed that by the time you paid £4 for that, £4 for the connectors, how many pounds for a bit of coax, a few more pounds for something else, and something else, and something else, and something else?
It all adds up. Yeah, it does all add up. But what I was trying to get to there, that is just unscrew it. So that's an F-type to SMA adapter. Again, a flea bay job, but it allows you to use the cheap coax with the cheap connectors to bring it straight in onto you can bring it straight into the RTL dongle with that quite easily. Because otherwise you're left facing an SMA connector here and an F-type connector there, and you're going to have to convert at some point.
Okay. Well, thank you very much, John. Thank you.
That's right.
Okay. Shall we set the date and time for the next meeting?